Welcome to today's webinar with the title Design of Single Foundations According to Eurocode in RFEM and RSTAB. My name is Moritz Bertram and I will lead through the webinar today. My colleague, Paul Kiedoch, is responsible for the development of the module and he will answer your questions today. We will have a quick look at the agenda. First, we will look at the features in the add-on module Foundation Pro. Then I will do a presentation of the add-on module Foundation Pro using a practical example. We will do a design according to Eurocode 2 for the concrete design and for Eurocode 7 for the geotechnical analyses. And also I will give you some hints regarding the documentation of the results. Next we go into the features of Foundation Pro. We have several types of foundations. First is the foundation plate, reinforced or non-reinforced. Then we have a bucket foundation with smooth and rough bucket sides, and also a block foundation, again with smooth and rough bucket sides. We can do a design, or we will do a design according to Eurocode 2 and Eurocode 7. The analysis done for the Eurocode 7 is the equilibrium limit state, then the uplift limit state, ground failure. We look at loads with large eccentricities. If we use the German annex, we can also look at a highly eccentric loading in the core. We do the proof for sliding, and the newest feature in Foundation Pro is the settlement calculation. And for the concrete design, we do a flexural design of the plate and the bucket, and also a punching shear design of the plate. What we can do in Foundation Pro is, for example, define soil profiles. As you see on the right side in the picture, we can define several layers of soil with groundwater for the geotechnical analysis and the settlement calculation. The dimensions of the foundations can be determined by the module. Foundation Pro makes a proposal which we can modify later on. Then we have the possibility to create a library of regularly used foundations, so you can just pick and modify a predefined foundation. Then the foundations with the reinforcement can be rendered by the module. As you see on the pic in the upper right corner, which is also shown in the presentation. And we have an option to show a detailed steel schedule and the concrete cubage in the module. Now we look into the model. It's a steel hull. The combination, the loading and the determination of internal forces are not subject of this webinar. They have been prepared beforehand as basis of this webinar. In the global X direction, this way, the construction is braced using fixed supports at the foot of the columns, while in the longitudinal direction, in global Y direction, a wind bracing is used. Subsequently, I want to design the foundations at the nodal supports using the add-on module Foundation Pro. in preparation of the webinar, I've already had a look at the column basis and have done a calculation using joints to determine the required bucket depth, which has to be 80 centimeters deep. Oh, I just see I haven't done the calculation yet, so I'll just let that run through. We have to determine the internal forces, otherwise we can't do any determination of the foundations. So this will just take a few seconds. Okay, now the joints calculation, and the program is done with the calculation. I go into joints again and have a go to the geometry, and the internal and external bucket depth is at 800 millimeters, 0.8 meters. Okay, with that I can go into Foundation Pro, which is opened, and here the first thing I want to do is select the nodes for the fixed supports. By default, all nodal supports are selected in the beginning, and I want to deselect some of them. The gable supports are going to be calculated later on. Okay, and now I have only the fixed nodes. The selection of, then we have to do the selection of the foundation type. In this case, this is supposed to be a block foundation with smooth bucket sides. The pick on the right side changes. The next thing we have to do is go on with the definition of the allowable soil pressure. We have two different options here. For one, we could use a user-defined maximum soil pressure from a geological survey, which has been done before, or we can use the bearing capacity according to Eurocode 7 Annex D, which is the default setting, and we will leave that there. For the correct determination of the bearing capacity, I have to provide some soil parameters. At first I have to select the subsoil conditions, either drained or undrained conditions. We leave it at drained conditions, which is the default setting. And then we go on to the definition of the soil profile with the button Edit Soil Profile. Default is a soil profile with a thickness of 10 meters with a default material that is defined in the box on the left and closely defined on the box in the box on the bottom. For the first layer, I will leave the material and change the thickness to 1.1 meter. I can delete the earth covering because that's not correct in our case. And you see, as soon as I hit the next line, the picture on the right side changes, so I'm always in control of what I'm entering into the table. For the second layer, I also leave it at the soil that has been pre-selected. The thickness of this layer is supposed to be 1 meter. Then for the third layer, I'll select silty sand from the material library with a thickness of 0.25 meters. Then we'll have a silt with a low plasticity and a thickness of 50 centimeters. And the last layer is going to be gravel and gravel sand clay mixture with a thickness of 7.15 meters. So I get to a total thickness of 10 meters. On the right side you see our soil profile, and don't get confused by the dimensions of the foundation in the picture. These are the dimensions at the start of the iteration, and after the calculation this will look more realistic. You can also turn on and off the measurements in this picture to which show you the height of the layers below the ground level. Alternatively, you can turn on a numbering of the layers associated with the tables, the table of the soil profile on the left side. You can adjust the picture to your needs and print it to the printout report using the print button down here, and thus supplement and loosen up the default tables in the printout report. So we are finished with the soil profile and go on to the next window, 1.2, geometry. Here we can take over the dimensions of the columns of the cross sections via this button, import column dimensions from RSTAB. The module gets the outer measurements directly from the main program. This could be used directly, but we have done the design of the column before and used the base plate with a size of 35 by 35 centimeters. I'm free to just adjust that. The main influence of that side is on the punching shear design, since the punching cone depends on the dimensions of the column. Then we go on to the definition of the foundation plate dimensions. If you already have a clue what the dimensions of your foundation are, they can be defined directly. The default setting is the automatic determination of the required dimensions via rate, which we are going to use. We have predefined starting measurements of the plate. Depending on the loading and the foundation type, the size is increased iteratively until all the proofs are met, all the geotechnical proofs. The starting size is 1.05 by 1.05 with a thickness of 20 centimeters, and I can adjust that. So I go to edit the design parameters for the foundation plate, and I get a new dialog. Here the minimum dimensions are shown. I could change these, but I'll leave them there. The plate thickness at the start of the iteration is a little too thin for my needs, so I go to 0.3 meters. As a next step, we can define in which direction the module increases the size of the foundation plate to fulfill the design criteria. In our case, the fixation of the support is for the moment about the y-axis, so therefore an increase in the x direction is the most reasonable. If we make that bigger, the foundation will be better. So only the side length x shall be increased. That means delta y is grayed out. The default increment of the increase is 5 centimeters, and we leave that. If the geotechnical proofs are not met, I can also adjust the Z direction of the foundation plate by several means. I can increase the thickness of the foundation plate. I can increase the height of the earth covering, or I can just do no increase and only increase the side length x, which I want to do. So no increase in that dimension. Below that we have additional settings for the sliding resistance design. This is grayed out because this is only active if a passive soil pressure is considered, and this can be activated in window 1.1 general data. So we close the dialog with OK and go on with the definition of the dimensions of the bucket. We have a minimum bucket depth of 80 centimeters from the joint design, and we take that for the bucket height and the embedment depth of the column. And we want to have a vertical sides of the bucket with a bucket inclination of 90 degrees. So the column allowance at the top and at the bottom have to be the same, so I put in 10 centimeters for all of them. So much for the geometry. The next window is 1.3, materials. The concrete is at C2530 and the steel is a B500S, so very common. The concrete covers can be freely defined, or you can activate the option minimum cover according to standard, what we will do. And we have to verify that we have selected the correct exposure class and we can do that under edit. For foundations, this should be XC2, and we leave that there. Confirm with OK. The last inputs I want to make in this dialog are for the available reinforcing steel mats and the reinforcing bars respectively. I don't want to use any mats, so I can deactivate them. And I want to use reinforcing bars from 8 to 14 millimeters diameter. And so I'm done with the material, and I'm going on to the loading. At the top of this window you find 4 tabs: structural and geotechnical, uplift, static equilibrium, and characteristic values. The number of the tabs depends on the selected analyses, and we will have a quick look at the details down here. Here we can select which geotechnical and concrete designs must be done. So in this case I have already checked the uplift beforehand, and I know that there's no uplift problem for this structure. Also, I don't have any groundwater above the bottom of my foundation, so I can uncheck the uplift design. This has an influence on the tabs. In window 1.4 loading, the uplift tab will vanish after I click OK. A few more notes regarding the details. The check for the punching design can be activated if it's not necessary. Also, the flexural design of the bucket or the plate cannot be activated. They will always be done depending on the type of foundation. On the lower right, I can deactivate single components of the support forces. For example, if I connect the foundations using a strip foundation or a flexible foundation beam, it's possible to deactivate a component, for example, PY. And here I can also select if only forces in plus Y direction or in minus Y or in both directions shall be deactivated. We will take all into account, so we activate all. Then we click OK. The tab for the uplift has vanished, and now we have to select the load combinations for our designs. For the ultimate limit state, we want to use the strength combinations. We could put them in one by one, or we can just use the filter down here, select all combinations for the ultimate limit state, and send them over to selected for design completely. I do the same for the static equilibrium, combinations ULS, EQ, send them over. And for the characteristic values, serviceability limit state characteristic, and send them over. Now we are pretty much done with the loading. We could enter some additional loading. For example, if I have a foundation slab above this foundation, of which I want to take the self-weight into account, we could do that down here. You see all the possible additional loads in the picture, but we don't want to do that now. So we are finished with the input for the first foundation, and we can start the calculation with the button calculation. The internal forces have already been calculated. The program initially determines the foundation dimensions, so the geotechnical proofs are met, and after that the concrete design is performed. The program sends us right to 2.1 geometry, which are the results now. Here we can see the determined foundation dimensions. I can also show them in the picture on the right side. We have an X direction of 1.75 meters, Y 1.05 meters, and a thickness of 1.04 meters. These are the dimensions which the program calculated due to my specifications regarding the determination process. Now I can go ahead and round up the values. So I go back to 1.2 geometry and use the button Import Dimensions of Foundation Plate from Calculation. So the program gets the values from the results of the first calculation. You see 1.75, 1.05 and 1.04, and I round them up to 1.1 meters for the Y direction and 1.1 meters for the thickness. Now I have to redo the calculation because I have to approve that my design is still valid with these new values. So I get the new values in the results table and I can go on. Now I go to governing design criteria on the left side, table or window 2.2, governing design criteria. All the design criteria with the corresponding utilizations are shown here. If I click on one criterion, for example 0.9542 for the equilibrium limit state, this is also my maximum criterion. Then I can, for example, show the load constellation in the picture on the right side, on the bottom right, and I can look at the details in the table down here. For example, for the resulting moment at the edge number 3, which is my criterion, and I have a stabilizing moment of 105.25 kilonewton meters and a destabilizing moment of 99.19 kilonewton meters. And it's the same procedure for all the other criteria. Then I have window 2.3, required reinforcement, similar procedure as in window 2.2. We have different reinforcement for the foundation plate and the buckets. The foundation plate is the first 6, and for the bucket we have the lower 4, bending reinforcement and horizontal and vertical stirrups for the bucket. Then we have, if we select a certain line in the table, the details are shown in the lower part of the windows, and I can also show the corresponding loading in the bottom right picture. Then we have the windows 2.4 and 2.5 for the plate reinforcement at the bottom and at the top, and we have a reinforcement of 8 millimeters and 25 centimeters for all of these. If that's not what I want, I can click on different reinforcement proposal and select a different size or distance for the reinforcement bars. For this example, the reinforcement proposal is okay, and I can skip to change something? No. To 2.6, bucket reinforcement. Here you see the proposed reinforcement for the bucket in the picture and also in the table above. If you want to change the proposal, you can do so in the table by changing the values in the white cells. If you do change anything, then you have to recalculate to assure that everything is still within the limits. And then we have the windows 2.7 and 2.8. The steel schedule and the concrete cubage. We have 10 foundations in 10 nodes, and the steel schedule shows me the number of rebars per foundation and the total number for all the foundations and a total mass of reinforcing steel on the lower right. Similar, it's for the concrete cubage. We have a volume of all foundations of 18.76 cubic meters and some additional concrete as backfill concrete to fill the space between the bucket walls and the column. Both the steel schedule and the concrete cubage can be selected for the documentation in the printout report. Now I want to show you these 3 buttons on the bottom down here. First is the 3D rendering. Here I can show my whole foundation, including the dimensions if I want to. I can show or not show the reinforcement on top and bottom and for the bucket. And so I can check everything if it meets my requirements. Also, the soil profile can be shown besides the foundation, and if I've turned everything as I needed, maybe without the perspective, I can print it to my printout report using the print graphic button. Now I close it and I open the drawings. Here, as mentioned before, the module Foundation makes a proposal on how to realize the reinforcement. Under the button drawings, we find the different reinforcement drawings. Over the different buttons up here, I can show these drawings, including the sections, to have a look at what the module used for the design, which can be a help for further reinforcement detailing. And these drawings can also be exported as a DXF, going over File, DXF export of reinforcement drawings, and then they can be used for further detailing, for example using AutoCAD. And the last is the graphics button. If I hit that one, the program skips to the main program and shows me all the foundations that I've calculated so far. And we also see that the supports supports for the gable, we don't have any foundations yet. So I go back into the Foundation Pro module using this button in the panel, and I make a new foundation using the copy function, since I don't want to make all the entries again. So copy the current foundation. The module automatically recognizes the nodes that have not yet been designed. The only thing that I have to do in this window is switch from the block foundation with smooth bucket sides to the foundation plate. Okay, everything else is left without change, and I go to the geometry in window 1.2. Here I can take over the dimensions from the column again, which I make 20 by 20 now. The foundation plate is not determined by the program now, but I want to check if it's enough if I have a cube of 0.8 by 0.8 by 0.8 meters. Oh, and now I see I've entered 0.8 and there's a 1.8 left. So if I try to enter that size, the module automatically recognizes that the punching cone must be inside the plate. To be able to enter the size of 80 centimeters, I have to go into the details and check that it's supposed to be a non-reinforced foundation without bending reinforcement according to 12.9.3. When I do that, the punching design, including the iteration of the control parameter, is automatically deactivated, and after clicking OK, I can enter the 80 centimeters for the side lengths. We don't have any bucket, so we don't need to go on with that. The next window is the materials window. We don't have any steel since it's an unreinforced foundation, and we leave the concrete at C2530. So we can go to loading. This has been copied from the first foundation, so everything is set as required. And I go ahead and start the calculation. It's not taking that long since there are no concrete designs to be done. I go to the governing design criteria, and the maximum criterion is again for the equilibrium limit state with about 80%, which is fine for me, so I can leave that there. And over the graphics button I go back to RSTAB and I see my cubic foundations for the gable columns. The last part of the presentation is the settlement calculation, which I already mentioned starting the presentation. I go back into Foundation Pro and there I activate the settlement calculation for foundation number 1. I go into details, check settlement, click OK. And now I can set a limit for the deformation of the foundation in window 1.1. The default is quite big at 120 millimeters. So I adjust to 10 millimeters and check if this requirement is met. Do the calculation. Exactly. I haven't added any loading, and I wasn't really done anyway. So I go back to general data. No. Number 1, details. Okay, settlement, 10 millimeters. The limit inclination is related to the single foundation slab, not to the complete structure, which could be calculated over the different settlements of the single foundations. Another thing to keep in mind when doing this settlement calculation is the loading, which I had just forgotten. So if we go to the 1.4 loading, I get a new tab which was activated when we activated the settlement calculation, and for that calculation we want to use the combination number 49, quasi-permanent. The calculation is basically the same as in the first calculation cycle. All designs are calculated again, and in addition we have a criterion for the settlement in window 2.2. So we go to governing design criteria. Here is the settlement. It's at about 21%. And in the picture you can now also see, if you click on criterion down here, the subsidence basin developing below the foundation. This looks like doing like the modules doing calculation using a flexible foundation slab, but if you see this message 211, this means the calculated plate stiffness is greater than 1.0. The plate is solid. The calculation as a solid plate is of course also possible. So I go back to the details and go to the settlement settings down here. And here I can activate the iterative calculation of contact pressure for solid foundation plate. Okay. Okay, and I start the calculation again. The program initially starts with the calculation of a flexible foundation and then calculates again at the decisive node with a solid foundation, and the plane settlement at node 40 is now at 1.4 millimeters, and this is a plane surface now. In the details, you can now show the spring constant for this node. Down here, you find the spring constants for the vertical spring and the spring constants about the x and the y-axis. So I can confirm that with OK. No, not yet. I forgot. I can also export these support spring constants to RSTAB. This would require all the results to be deleted because we change the model itself. So we click OK and close the module, and now we can have a look at the at this node number 40 at the nodal support. Double click on that one, and we see there's a new type of support. And if we have a look at the specifications of this support, we see the spring constants that have been exported from the module. So if you want to do that not only for the decisive node but for all nodal supports, you would have to do the calculation with a solid foundations for all the nodes, and you would have to export the spring constants for all the nodal supports. That's it for the presentation. Of course, everything I've shown in RSTAB is also possible with RFEM and the add-on module RF Foundation Pro. It's basically the same. For those who have not yet used our programs, feel free to download the trial version from our website. Up here, download trial versions, then you get to this site, and all our programs are available with a full functionality for 90 days, which you can use to test the programs thoroughly. Thank you, Paul, for your assistance and for answering the questions. If you didn't get an answer yet, we will follow up, sending you emails. Thank you for your attention and have a nice day. Bye.